Okay, I thought about it, and I'm not going to do another just Laplace transform from scratch. The two problems I've done, they're really all the same. You go through. So here was the problem we had last time. Here's the differential equation, and we came up with this piece here. All right, y of s, transfer function times input, and then here's all our initial condition stuff. And so what I'm going to do now is I want to show you the connections between Laplace transforms and differential equations and convolution. We're going to tie them all together. All right. So if you look at this, if somebody gave you the transfer function, s plus 6 over s cubed plus 6s squared plus 11s plus 6, and you compare that to the differential equation, they're kind of the same thing. All right. If you simply replace x dot becomes s x of s, then this 11 y dot becomes 11s y of s, 6s squared y of s, and then s cubed y of s. All right. All of that's in here. You can look at this and go, oh, y of s. So this is y triple dot plus 6y double dot plus 11y dot plus 6y equals x dot plus 6s. You can read, when you're looking at in Laplace, this transfer function, it is the differential equation. It's right here, right in front of your eyes. All right. Well, let's just see where that can take us. Uh, so let's see what we have now. Relative to the forced response, input times transfer function gives us output, namely the forced response output. Okay. And we've looked at responses for the input of a unit step. Laplace transform unit step input is 1 over s. We've used it. Now, what's the Laplace transform? What about the unit impulse input? So I said I used to work at GM, and we would bash things with sledgehammers. Those are very much impulsive inputs. Uh, so what about this? So we need to get the Laplace transform of that. And this is really interesting. Uh, Laplace transform of the delta function, or impulsive input, equals integral 0 to infinity delta function e to the minus st dt. But this is the sifting property. It only exists at t equals 0. If t equals 0, you'd have e to the 0. It's a 1. Integral from 0 to 0 plus of the 1. Okay, this has, remember, when you integrate this, this has area 1 somehow. But you get a 1. This is fascinating in a sick way if you really like all of this fun math. Here's an impulse in time. So we have delta of s is equals 1. And you're going, okay, why? Well, because of this. If I have, okay, this is a Laplace transform of a unit impulse times a transfer function, that's just 1. In general, if I have an impulse times a transfer function, it gives me the impulse response. But this is 1. So here's the wild thing. This TF of S I just showed you a moment ago is nothing but the differential equation. You can back it out instantly or bloody quick. It's also the Laplace transform of the impulse response. All right? Because the Laplace transform of impulse is just 1. And you might go, okay, well, but notice how we've solved these problems. It's input of S times impulse response of S. We used to call this just the transfer function, but we'll note the transfer function is nothing but the impulse response put in terms of S. So here we have impulse input of S times impulse of S equals forced response. Well, that looks a lot like convolution. Input, impulse response. Remember all that we did when we did convolution? We took the input, did a flip and slide, and we multiplied that by the impulse response and took the integral. So if y of t is the convolution of input and impulse response, then here's the question. Is the Laplace transform of y of t, which will be by definition called I of s, is that just equal to I of s times s of s? Laplace transform of the input times the Laplace transform of the impulse response. And the answer is yes. So a Laplace transform is nothing but the convolution integral. But we don't have to set up all these crazy integrals and slide them through in time and do all of the stuff we had to do. When we simply form all these s's and multiply them together, we have accomplished what this convolution integral does. It is the same thing. And then we take all our s's once we've multiplied them and they equal y of s, and we do inverse Laplace transform by all our partial fraction expansions, and then we get our response in time. So through the Laplace transform, we can see how our transfer function is nothing but the differential equation and is nothing but the Laplace transform of the impulse response. These things are all totally related. Now, I am not going to make you do this on an exam. I'm not going to hold you accountable, but there's always an element to people who are like, prove that to me. Fair play. So stop the video. Here is the integral, the proof of this, going through all the integration. If you want to follow this, and you can go through it, and you will wind up showing that this is nothing but the Laplace transform of the input times the Laplace transform of the impulse response. If you want to see that, it's all here. Follow it through. I'll leave that to you. And with that, I will be stopping this video. And so the next stuff we're going to do in terms of understanding what Laplace does, how to use it, the sort of the three-step process to, or two-step process, depending on how you look at it, to solve differential equations. We're done with that. So now we're going to start analyzing the transfer functions. So that's what's going to come up next. And so we're going to focus on that for a while. And when we're done with all of that, then it's going to be time to start modeling mechanical systems and developing differential equations. We'll talk more next time.